Now let's put all of that together, all those little pieces of algorithm, put them together and create the script or the program for the Gaussian elimination in Octave. Now one thing we're going to do a little different here is that the matrix from the system, we're going to split that into two matrices, the matrix of coefficients and then the right hand side. If you remember before, we used the entire system, all those coefficients from the system, we put that in matrix A. So previously the matrix A had 5 columns. These 4 columns from the coefficients, and then there was an extra column here for the right hand side. But we'll see later that splitting into 2 will be easier. To understand, and we're going to do other things with the matrix A of coefficients, matrix of the coefficients, and the right hand side as separate objects. So for the matrix A, we enter simply that. Let me show you how to enter the right hand side. We can put that in a vector B, or matrix B. That will have only one column. So I can write B equals square bracket and then -3. And we use semicolon, meaning that we're going to move to an extra row. If we don't put a semicolon, then Octave is going to think that this is still one row. You're still typing things on one row. But it's just -3 in one row, and then 1 in the second row, 4 in the third row, and then 4 in the last row. Close bracket, and that's the vector B. All right. Okay. Now let's go back here to our algorithm that we saw, the pieces of the algorithm. This is the elimination, the Gaussian elimination, and here's the backwards substitution. So we type that in Octave. Let's see how we can do that. So here is ge.m, so I created that file. I'll just type function and then x equals to ge. And the input, or the parameters that we're going to use when we call this ge function, we have to provide the matrix A of the coefficients and the vector B, that's the right hand side of the matrix. Also, we need to tell Octave what this variable n is. N is the number of variables in the system. If you have the matrix of the coefficients, it's simply the number of rows in the matrix. So I'll give an example here. The matrix A in this example has 4 rows and 4 columns. There is a function in Octave called size. If you put size in parentheses A, that gives you the size of the matrix. It's a 4 by 4 matrix. So the first number is the number of rows, the second number is the number of columns. And we only need one of these two numbers. We can simply do size A, comma 1. That will give you the first number. Or you can use size A, comma 2. That will give you the second number. But they're the same. So we're going to put that and tell Octave what the variable n is. N is size of A, comma 1. So that will give you the number of rows of the matrix. Now let's put the loop here, j. It goes from 1 to n minus 1. And then here's another loop. It's inside the loop j. Now this loop here goes from j plus 1 to n. Okay. So the colon here is meaning that its destinations from 1 to all the way to the last number here. Okay, and then here we're going to put row I. If you remember how we access row I of a matrix, it's like that. That's row I of the matrix A. Row I would be row I minus that constant, or that coefficient here. We're going to go ahead and put this in a variable because we're going to use that also to deal with the right hand side. So we can go ahead and let's put that in here. Let's define the variable mult. Okay, mult is a ij and divided by a jj. And then here we can simply say minus mult times, now it's row j. Here it is. Okay. Now, here we are eliminating, we are dealing with the entire row of a matrix, of the matrix A, but matrix A now has only the coefficients of system, the coefficients of the variables. Notice that the right hand side is also part of a row, right? So we have row 2, it's the second row is 2, 1, negative 1, 1, and this one here. So this one has to participate also. When we multiply the entire row by something, this number needs to be multiplied by that same thing. So whatever we do to row I, we have to do also to the coefficient here bi, right? This is b1, b2, b3, b4. We have to do that to bi, and so we need to put that in here, right? I could maybe squeeze that in here, right? bi is bi minus, and then the same thing here, mod in times bj. Okay, let's put that in octave here. bi equals to bi minus mod times bj. Now we can close the inner loop, and then close the outer loop. Should be N4. Okay, that eliminates. That does the Gaussian elimination. Now, before we type the back substitution, let's go ahead and output here the matrix A and the vector B and see how they look like. And so this function is not finished yet, so we're going to stop here and put the back substitution later. I want to show you how it looks at this point, how the function works at this point. Okay, we have the matrix A, it's there, vector B. Let's call the Gaussian elimination. So this is A, comma B. Alright, so notice that, see, look at the the matrix A got eliminated, and look at the right hand side, it's changed, right? It's remember we had the negative 13 divided by negative 13, if you remember that. So it seems like it's working. Alright, let's go back here and then finish the script. So now it's a backward substitution. So here we're going to do for I equals to n to 1. Now Octave, when Octave sees that a loop is going from a number greater than 1 back to 1, Octave gets confused with that. We have to tell Octave that we are going backwards. So that's why we put a negative 1 colon here. Okay, so this is called a step. It tells Octave how you're going from n to 1. You're going by negative 1. You're going, so if n is 4 in this, 4 to 1, then you start with 4, and then minus 1 is 3, minus 1 is 2, minus 1 is 1. It tells Octave how to get from n to 1. That's simply what it is. Okay, here's the inner loop. It's I plus 1 to n. And then here we're going to change bi minus, and then here is the coefficient of the matrix, the entry ij times the variable xj. Okay. All right. And then here we're going to end the loop, the inner loop. Now we're going to put xi equals to bi divided by ai. That's the end. And so we're defining the variable x here. Octave is going to output the vector x. You see, at this point, x is a vector, right? We are defining x1, x2, x3, x4. And Octave is, here in this function, we are defining the vector x. That's all we need. So let's save that. And then let's run GE again. There it is. That's the solution. Negative 1, 2, 0, 0. Okay. And we can check that real quick. So x1 is negative 1, so we put that in here. 3 times negative 1 minus 2, right? x2 is 2, minus x3 is 0, plus 2 times x4. Yeah, that looks like it's working. Right? Negative 3 minus 2 plus 2 is negative 3, so it's good. Let's check the second row here real quick. 1 plus plus 2, right? Plus 2 minus x3 plus x4. Negative 2 plus 2 is 0, plus 1 is 1. Yeah, it's working. Alright, so it seems like it is working. Negative 1 plus 2 and 0 here. 3 times x4, that's 3 times 1. That's 1 plus 3, that's 4. Great. Alright, I want to check the last one. It seems like it's working fine. And now one final thing I want to say here. Notice that when we run a function, there are several things that show up on the screen here. Too much garbage. I guess we don't need to see all of that. When you're typing a function in Octave or any command, if you don't want to see the output, then you can put a semicolon at the end. So you see here, all of these commands, it shows up on the screen. The result shows up on the screen, like the n equals the size of a, comma 1. That shows up right here. So let me clear the screen here and run that again. Okay. There it is. See? N equals 4. That's the output. That's the output of this command here. And then it shows the matrix A every time. Let's see, here's mot. It's 0.6667. That comes from this command here. And then when we do something to even to one row of the matrix, Octave shows the entire matrix. And then if we do something to the vector B, it shows the vector B here. And then the loop goes back, and then here's mot again. If you don't want to see all of that garbage, unless you want to see that, but if you don't, you can simply put semicolon at the end. You don't need semicolon here for 4 or and 4. You don't need that. But at the end here, at the end there, at the end here, and then this one here as well. Any operation, arithmetic operation or assignment, Octave will output that result. So we can put all these semicolons, and then look what happens. So let me clear the screen here. CLC clears the screen. I'm going to run G again. See? Octave only outputs the variable x or the vector x at the end. So you don't need to see all of what is going on behind the scenes. Okay?